Hello everyone, this is Nahin from Oklahoma State University. Today I am going to present about a safety-aware model-based reinforcement learning framework for systems with uncertainties. This is a joint work with Catherine Harland, Dr. Kamala Purkar from Oklahoma State University, and Dr. Nevinson and Dr. Bell from AFRL. What has motivated us to do this work? Deployment of autonomous systems in complex, high-risk tasks provides significant operational benefits such as accuracy, physical endurance, and so on. However, autonomous systems need the ability to synthesize and execute safe control policies online and in real time. To improve robustness to parametric uncertainties, modeling uncertainties are motivated by tasks that require systems to operate in dynamic environments with changing objectives. Autonomous systems need the ability to perform desired tasks in the presence of parametric uncertainties while remaining safe. These facts have motivated us to develop new methods for safe learning. Over the past few decades, reinforcement learning has been established as an effective tool for optimal control policy synthesis for both known and uncertain dynamical systems. RL typically requires a large number of iterations due to sample inefficiency. Sample efficiency in reinforcement learning can be improved using model-based reinforcement learning. However, model-based reinforcement learning methods are prone to failure due to inaccurate models. In the past, model-based reinforcement learning techniques under the umbrella of ADP have been successfully utilized to solve reinforcement learning problems online with model uncertainty. ADP utilizes parametric methods such as neural networks to approximate the value function and the system model online. By obtaining an approximate of both the value function and the model system model, a stable closed-loop adaptive control policy can be developed. In addition to the closed-loop stability, safety is also a significant consideration for online reinforcement learning problems. Real-world optimal control applications typically include constraints on states or inputs that are critical for safety. Recently, ADP has been applied to both input and state constant optimal control problem. The state constant optimal control problem was transformed using a barriers transformation into an equivalent unconstant optimization problem. A model-based reinforcement learning approach to address the state constant optimal control problem appeared where the results are extended to soften the restrictive persistence of excitation requirement. However, the methods developed in past required fully known models, which is often difficult to obtain. In this paper, a reinforcement learning technique is developed for barrier transformed safety critical systems, which utilize a novel filtered concurrent learning method to realize simultaneous learning and control in the presence of parametric uncertainty. Now we are going to talk about the problem formulation. Consider a continuous time affine nonlinear dynamical system x dot equal to f theta plus gu, where x is the system state, theta are the unknown parameters, u is the control input, f and g are known local Lipschitz functions. Now our objective is to design a controller u such as starting from a given feasible initial condition x naught, the solution decays to the origin. The solution will be always in a user specific bound from small a to capital A. Now what is the barrier transformation? These are the definitions of barrier function, inverse barrier function, and barrier transformation. Now barrier transformations dynamics will be s dot equal to fs plus gu. Now we have developed a lemma, and that is the safety that this lemma implies that a feedback controller that practically stabilizes the transformed system, then the same feedback, if a feedback controller that practically stabilizes the transformed system, then the same feedback controller applied to the original system by inverting the barrier transformation also stabilize the original system. This lemma also implies that it will guarantee safety of the original system. Now, the objective here is to determine a controller U that minimizes the infinite horizon cost functional, where R is the combination of state penalty and control penalty. One way to characterize the solution of the optimal control problem is using the value function. The optimal value function denoted by V star here, and provided the optimal control policy exists, the value function is characterized by the corresponding HJV equation. If the value function is continuously differentiable, then it can be shown to be the unique positive definite solution of the HJV equation and provides the optimal closed loop policy. Now, since computation of analytical solutions of the HJV equation is generally infeasible, especially for systems with uncertainty, parametric approximation methods are used to approximate the value function V star and the optimal policy U star. We have used the linear in the parameter approximate method inspired from the universal function approximation property of single layer neural network in this paper. Since the ideal weights W are unknown, an actor-critic approach is used in the following to estimate W, where the critics weight WC and the actor weights WA are estimated of the ideal weights W. Now, substituting value function with the estimated value functions using critical weight and controller with the estimated controller using the actor critic in HJV equation yields Bellman error. Traditionally, online reinforcement learning methods required a persistence of excitation PE condition to be able to learn the approximate control policy U, guaranteeing PE a priori and verifying P online are both typically impossible. However, using virtual excitation facilitated by model-based BE, a Bellman error extrapolation, stability and convergence of online reinforcement learning can established under a P condition like that. P-like condition. Well, impossible to guarantee a priori, it can be verified online. Using the model system model, a Bellman error can be evaluated at any arbitrary point in the state space. Virtual excitation can then be implemented by selecting a set of states and evaluating the Bellman error at this set of states to yield extrapolated Bellman error. Since the Bellman error depends on the unknown parameters theta in this model, in the system model, we designed a novel parameter estimator to learn the theta online. Estimates of the unknown parameters theta are generated using the filter. The filter is motivated by the fact that if the matrix scripted y transport scripted y is positive definite, then we can do the Lyapunov analysis to establish convergence of the parameter estimation error to origin. Initially, scripted y transport scripted y is a matrix of 0. Now we need to impose a finite excitation condition, and that is the assumption that there exists a time instant t greater than 0 such that scripted y is full ranked. Now, like similar to other model-based reinforcement learning methods that rely on system identification, we also need to have this assumption as well, the second assumption as well. If a feedback controller that satisfied assumption is not known, Then, with the additional assumption that the state trajectories are excited over the interval 0 to t, we all we can also have another controller that can be learned online using model-free reinforcement learning. This is our fully developed framework. And in simulation, we have considered two-state dynamical system x dot equal to f theta plus gu, and these are initial conditions. The top left figure shows that the system state x stays within the user specified safe set while converging to the origin. The top right figure shows that the unknown weights for both the actor and critic neural networks converge to the similar value. Our bottom left figure shows that the parameter estimation errors also converge to the zero, and bottom right figure shows a comparison between GPUB and our system. Now, in summary, the control synthesis challenges for safety critical systems are parametric uncertainty, output feedback, partial output feedback on model dynamics. And we have done our contribution of this paper is novel implementation of barrier transformation in deterministic nonlinear systems with parametric uncertainty, novel filtered concurrent learning based system identification, theoretical results to guarantee safety using barrier transformation for systems with parametric uncertainty. Limitations of our method: barrier transformation, box constraint, model-based reinforcement learning. It is almost impossible to obtain the exact basic functions. Possible and safety guarantee: the possible violation due to the unmodeled dynamics, stability, local stability results. Thank you. Any questions?